Seems I'll need to keep a closer eye on this camera. It tends to cut out every now and then because, therefore, the mass of a hydrogen atom and the masses of all other atoms are kind of molecules is up when we start talking about Low-Schmidt, because then we talked about the molecules of and the molecular chemistry and the definition of the mole and the gram atom in terms of the diatomic oxygen and the monatomic oxygen, and with regards to usually in the presence of a gas that there's something like the diatomic of the gases like oxygen and hydrogen, that each gram atom of a univalent element is associated with a certain quantity of electricity, 96,520 coulombs. But that this relationship that Faraday had discovered was providing what is a ratio, yet in the infinitesimally small, these electrical quantities where charge is a quantity, and these kinetic quantities where mass is a quantity. And that then I'll pick up reading where I left off as there was a little bit lost. The next advances were made in the domain of the theory of gases, raised to the status of an exact science as a result of the efforts of Maxwell Boltzmann and above all Clausius. And so Clausius is, for whom was coined entropy. And these days, well, entropy is a really great thing. It's something that in terms of the first law and the second law of thermodynamics being different and kind of having different definitions and different derivations makes it so that something along the lines of Clausius's entropy, while in all kinds of matters of the systems at rest, the closed systems that achieve to their equilibrium by a principle of least action in this thermodynamic entropy of the second law of thermodynamics. That there's, again, this molecular is an example of this outer product or emergent conditions that make it so that it's not always necessarily so that something like second law is really what holds true when something else holds true in any kind of interaction and dynamics, which makes things as they are. And then Heisenberg gets on to describing, again, the year 1865 brought a new achievement of considerable importance. The first is yet only an approximate determination by Low-Schmidt of the size of atoms, and hence of the number of molecules contained in a given volume. Low-Schmidt investigated the internal friction of gases, and this is basically why we have PV equals nRT, or the ideal gas law, vis-a-vis Boyle's gas law, and these kinds of things, which help express these, again, matters of proportion when their systems and their configuration or experiment are particularly well understood and well defined and constrained via particular easy forms to solve for, and their closed forms. The size of the atom has been known accurately for about 40 years, about 100 years ago. And these days, again, it reflects on the fact that these are running as constants and so on. Therefore, and then it was stated that individual atoms are completely invisible and it's impossible to observe them directly. And so at this point, then, we are going to go and read back again from Einstein, who had just kind of helped explain that according to the phenomenological access to these things, there really takes at least some level of object sense of these infinitesimals and their numbers to have anything beyond a finitist's incomplete view of the world. Kind of like in the story of the flat land, which is a story about a two-dimensional world, a flat land. And then the creatures that lived on flat land, like Triangle Man and Circle Man and this and that, when they encountered a four-dimensional object, had no idea particularly how it could behave because it was outside their entire milieu. But in this, there's a particular example of a kind of, three-dimensional and four-dimensional extension of that helps explains that the coordinates and the connections can so exist there as well as they can anywhere else. Then there's all these the dynamics and interactions can always be reflected as various forms of models of them. And so then when we get in today's modern superstring theory, which has got 11 or 12, or 26 different dimensions just to fill all this stuff up, let's make a big tent for all this stuff so that then we can stretch out and have all these different extrapolations built out and built into all these kinds of things. It's still just a three-dimensional space in one direction of array of time. But these other dynamics build up about the space-like and the light-like and the time-like, space-like, the time-like, and the light-like, which makes it so that these kinds of things still all fall together. So there's less to be said for the atomic model, and also the thinking what's underneath that, the elementary, fundamental, and the decomposition of those, where things need to be simple as they can be, simpler, and it's like and not simpler. These are the kinds of things that get into these usual fundamental discourses about foundations. Because it's a thing, and for our first principles and final causes, it ends up being as good as it gets. So the next chapter from Einstein is chapter 14. It says, the fundaments of theoretical physics. Science is the attempt to make the chaotic diversity of our sense experience correspond to a logically uniform system of thought. In this system, single experiences must be correlated with a theoretic structure in such a way that the resulting coordination is unique and convincing. The sense experiences are the given subject matter, but the theory that shall interpret them is man-made. It is the result of an extremely laborious process of adaptation. Hypothetical, never completely final, always subject to question and doubt. This is our scientific method that theories are not proven, they're just not disproven. They're not falsified. Falsifiability has arisen as that outside the empirical, because that means we don't know the fundamental, but you can have empirical theories, they're just not necessarily fundamental theories. And this is a book about the fundamental theories of physics, that for empirical theories and for fundamental theories, they both have the same criteria, which establish whether or not they hold true. That's that they're not falsified. And so just like a statistical hypothesis is always so that you never validate a statistical hypothesis, it's only not rejected. This is our statistical method, and it goes a long way into the soundness of it, because otherwise it's making decisions that would be described by causality, which is for the realm of mathematical proof. Then the entire idea of the ubiquitous success of mathematical physics is that the models are so that there is causality and provability in the models of mathematics and the objects of mathematics and logic, that then insofar as you apply that to the physical models, as we use the physical interpretation of these models as physical models, mathematical models, that the falsifiability attaches itself to the invalidation of the derivations, the mathematics. So some people say mathematics is the science of the infinite, but it's even more than that. It's the logic of the infinite. And then insofar as we can study and discover it, then there's various ways you can get into what are and aren't decidable things about the derivable things from the definable things, that definitions and their derivations that so follow, and their decidings of them, decisions of them, or judgments from the logic, are what make mathematics so ubiquitously successful. Then there's that statistics is essentially a branch of science, and that physics is essentially a branch of science, and it's pretty much so that the reproducibility of experiment is part of our scientific method, and the statistical hypothesis and statistical experiment is based upon, the criteria of sampling and the criteria of the design of the experiment, that both of them are involved in the design of the experiment, the sampling experiment, or the reproduction of a physical act, a configuration of experiment. They have the same fundamental criteria, the statistics and the statistical inference, and the physics and the physical inference, these things. So Einstein has just kind of said that. The sense experiences are the given subject matter, but the theory that shall interpret them is man-made. It is the result of an extremely laborious process of adaptation, hypothetical, never completely final, always subject to question and doubt. The scientific way of forming concepts differs from that which we use in our daily life. Not basically, but merely in the more precise definition of concepts and conclusions, more painstaking and systematic choice of experimental material, and greater logical economy. By this last, we mean the effort to reduce all concepts and correlations to as few as possible, logically independent, basic concepts and axioms. Though that what is truly fundamental is not necessarily that which isn't erased by the extensionality to things that can be called equal for all intents and purposes in the model, and their intentionality, which is that a bucket of apples and a bucket of oranges are each a bucket, but one's apples and one's oranges. They can be compared, but they do taste different. So that's just saying so that when we've reduced, for example, everything to a matter of energy, there's still that mass and charge are different kinds of quantities, and so is time. and so is radiation and so is color, basically. And so what we call physics comprises that group of natural sciences which base their concepts on measurements. So this is qualitative physics, and whose concepts and propositions lend themselves to mathematical formulation. It's mathematical physics. Its realm is accordingly defined as that part of the sum total of our knowledge which is capable of being expressed in mathematical terms. With the progress of science, the realm of physics has so expanded that it seems to be limited only by the limitations of the method itself, the limitations of the mathematics, and the limitations of the application of the model, and the limitations of the configuration of experiment, the cost of experiment, the energy of experiment. But it has expanded quite much in this realm that fundamentally the experiments and the higher order configuration and higher order energy have determined very strong bases for very fine or precise coordinates which define what to expect in all usual manners. That said, there's all kinds of systems in the nonlinear and hysteresis in the total, in this theory of sum potentials, which are not very tractable, if at all, or not very fungible, if at all, if they're even sensible at all. That the sensibility, fungibility, and tractability is still kind of the makes for the success of a model that in the theory is physics. The larger part of physical research is devoted to the development of various branches of physics. What are the branches of physics? Chemistry is mentioned, and there's electricity, magnetism, and kinetics. So there's mechanics, classical mechanics, E&M, chemistry, nuclear chemistry, radiochemistry. That's the same thing. There's anything to do with branches and fields in particular configurations. There's branches and fields, and this is the hard sciences. Social sciences are essentially involved with the non-qualitative, and it's not a matter of numerical things like infinity, and then also they are essentially arbitrary in many usual senses, or the models are always lacking compared to experimentation on humans and this kind of stuff, which is not unusual. Though that just like he said, that our practice of science is the usual practice of our inference compared to beliefs, desires, and motivations, specifically matters of belief, that then the hard sciences include all kinds of these branches of physics, that basically all hard sciences are branches of physics, in each of which the object is a theoretical understanding of more or less restricted fields of experience, and in each of which the laws and concepts remain as closely as possibly related to experience. These are his empirical fields. It is this department of science, with its ever-growing specialization, which has revolutionized practical life in the last centuries and given birth to the possibility that man may at last be freed from the burden of physical toil. I don't know if that's necessarily a good thing. On the other hand, because then physical toil would be free from him. On the other hand, from the very beginning, there has always been present the attempt to find a unifying theoretical basis for all these single sciences, consisting of a minimum of concepts and fundamental relationships from which all the concepts and relationships of the single disciplines might be derived by logical process. Now, this is kind of the idea of this axiomless natural deduction, to start even from none. And this is like the fundamental question of metaphysics of Nozick and Heidegger and many, many others. And that's really a thing for this to arrive at axiomless geometry, and to lift up above that from a mathematics to make for a hologram, which is a way to support space and time in one single continuum of numbers or mathematical objects, that makes that space and time naturally arises as a thing, and then that a whole Big Bang cosmology or steady state cosmology or cyclic cosmology kind of just arises as a thing, at least, that then that's so defined and builds up, and then it's just that the constants and numbers for things just end up being model fitting of a sort, that then of course is in terms of these fundamental interactions is what are defined and so carefully ascribed to by science, though that these laws of nature end up being reduced to more or less a law of logic. That is the thing. It's called foundations, mathematical foundations, logical foundations, and physical foundations together. Foundations. This is what we mean by the search for a foundation of the whole of physics. The confident belief that this ultimate goal may be reached is the chief source of the passionate devotion which has always animated the researcher. It is in this sense that the following observations are devoted to the foundations of physics. So foundations is the theory writ large. Then also there's the idea that a foundation is an independent corporation of people based on money or instruments of capital. And so that's the other usual interpretation of the word foundation as a noun is an independent, arbitrarily large body of capital in otherwise a realm of social things. But here it's foundations, the fundamental theories, and the fundamental theory. From what has been said, it is clear that the word foundations in its connection does not mean something analogous in all respects to the foundations of a building. Logically considered, of course, the very single laws of physics rest upon this foundation, but whereas a building may be seriously damaged by a heavy storm or spring flood, yet its foundations remain intact. In science, the logical foundation is always in greater peril from new experiences or new knowledge than are the branch disciplines with their closer experimental contexts. That is to say that it must encompass all known things, that it once it's found that there's something that's not explained by the foundations, then it becomes open, and what was closed becomes independent, and so that establishes grounds for a dialectic, and that is why that these various fundamental things are being reduced to their most simple relations, and then those add up to then where in extremis they are added up. So that's how this point and space become these complementary duals and form these kinds of things that make for a milieu that get past the inductive impasses either way, which makes for a deductive recourse, and that's part of foundations. If in the connection of the foundation with all the single parts lies its great significance, but likewise its greatest danger in face of any new factor. When we realize this, we are led to wonder why the so-called revolutionary epochs of the science of physics have not more often and more completely changed its foundation than has actually been the case. The first attempt to lay a uniform theoretical foundation was the work of Newton. In his system, everything is reduced to the following concepts. 1, mass points with invariable mass. 2, action and distance between any pair of mass points. 3, law of motion for the mass point. There was not, strictly speaking, any all-embracing foundation because an explicit law was formulated only for the actions at a distance of gravitation, while for other actions at a distance nothing was established a priori except the law of equality of actio and reactio. Moreover, Newton himself fully realized that time and space were essential elements as physically effective factors of a system, if only by implication. This is, as it only addresses motion of massy bodies, and not all that. Today we call that a platform or a plank of a discipline of a subfield of physics, but not foundations, no. It does, though, help to explain gravity and the usual notion of what goes up must come down, where the original foundation of reasoning and inference was that things change. Geometry is motion, and only constant is change. There were more abstract theoretical foundations, to be sure, and any theory of being is essentially a logical foundation with regards to that it's not necessarily complete or consistent, or that its axioms are independent, or that they are otherwise forming the desiderata requirements of a logical theory of everything, the logic. But it's still so that the answering of the fundamental question of metaphysics has been start of the dogma of all religious belief since antiquity. And creation, stories of creation. This Newtonian basis proved eminently fruitful and was regarded as final up to the end of the 19th century. It not only gave results for the movements of the heavenly bodies down to the most minute details, but also furnished a theory of the mechanics of discrete and continuous masses, a simple explanation, a principle of the conservation of energy, and a complete and brilliant theory of heat. The explanation of the facts of electrodynamics with the Newtonian system was more forced, at least convincing of all, from the very beginning was the theory of light. Newton was an interesting fellow, and though he took some experimental approaches others might consider risky or ill-advised, like when he wanted to determine how the eye worked optically, it's said that he took a blunt sewing needle and inserted it next to his eyeball and compressed his eye to see what it looked like when he compressed his own eye. Do not attempt that at home or anywhere. Do not stick anything in your ear sharper than your elbow. And also he was pretty well known that he was interested in alchemy, and so he'd burn lots of compounds and stuff, and that causes lots of problems. It's like one of my greatest instructors, the chemistry instructor, said, never sniff the compounds. If you must use your nose as a sensor, only barely waft it towards your nose and do not sniff the compounds. Back to Einstein. It is not surprising that Newton would not listen to a wave theory of light, for such a theory was most unsuited to his theoretical foundation. The assumption that space was filled with a medium consisting of material points that propagated light waves without exhibiting any other mechanical properties must have seemed to him quite artificial. Newton was pretty great, but he was also a great plagiarist. The strongest empirical arguments for the wave nature of light, fixed speeds of propagation, interference, diffraction, polarization, were either unknown or else not known in any well-ordered synthesis. He was justified in sticking to his corpuscular theory of light. During the 19th century, the dispute was settled in favor of the wave theory, yet no serious doubt of the mechanical foundations of physics arose, in the first place because nobody knew where to find a foundation of another sort. Only slowly, under the irresistible pressure of facts, there developed a new foundation of physics, field-physics. From Newton's time on, the theory of action at a distance was constantly found artificial. Efforts were not lacking to explain gravitation by a kinetic theory, that is, on the basis of collision forces of hypothetical mass particles. But the attempts were superficial and bore no fruit. The strange part played by space, or the inertial system, here Einstein now has replaced space with his parenthetical reference to the inertial system, within the mechanical foundations was also clearly recognized and criticized with especial clarity by Ernst Mach. The great change was brought about by Faraday, Maxwell, and Hertz. As a matter of fact, half unconsciously and against their will, all three of them throughout their lives considered themselves adherents of the mechanical theory. Hertz had found the simplest form of the equations of the electromagnetic field and declared that any theory leading to these equations was Maxwellian theory. Yet toward the end of his short life, he wrote a paper in which he presented as the foundation of physics a mechanical theory freed from the force concept. For us, who took in Faraday's ideas to speak with our mother's milk, it is hard to appreciate their greatness and audacity. Faraday must have grasped with unerring instinct the artificial nature of all attempts to refer electromagnetic phenomena to actions at a distance between electric particles reacting on each other. How was each single iron filing among a lot scattered on a piece of paper to know of the single electric particles running around in a nearby conductor? This is that magnetic force fields are interesting constant current. There's a supermodel for the otherwise that relation or the infalling, it is either powered by forces to the inductive magnet or for the permanent magnet that's baked in, literally, into the formation of the magnetic sites upon items according to the charge polarity in their kinetic forms. That it really is kinetics which build a permanent magnet, and it really is input to an electrical circuit which makes a magnetic field. These are well-known properties. So all these electric particles together seem to create in the surrounding space a condition which in turn produced a certain order in the filings. These spatial states, today called fields, if their geometrical structure and interdependent action were once rightly grasped, would, he was convinced, furnish the clue to the mysterious electromagnetic interactions. He conceived these fields as states of mechanical stress in a space-filling medium, similar to the states of stress in an elastically extended body. For at the time, this was the only way one could conceive of states that were apparently continuously distributed in space. The particular type of mechanical interpretation of these fields remain in the background, a sort of placation of the scientific conscience in view of the mechanical traditions of Faraday's time. With the help of these new field concepts, Faraday succeeded in forming a qualitative concept of the whole complex of electromagnetic effects discovered by him and his predecessors. The precise formulation of the time-space laws of those fields was the work of Maxwell. Imagine his feelings when the differential equations he had formulated proved to him that electromagnetic fields spread in the form of polarized waves and with the speed of light. Now here, again, electromagnetic fields and their interactions are bradyonic, slower than the speed of light, though arbitrarily fast, less than that. Whereas light is arbitrarily that the light in a vacuum is tachyonic to light in all other media. That light is different than electromagnetic and electromagnetic field interactions, though that radio waves travel at an arbitrarily large speed, less than that of light. To few men in the world has such an experience been vouchsafed. At that thrilling moment, he surely never guessed that the riddling nature of light, apparently so completely solved, would continue to baffle succeeding generations. Meanwhile, it took physicists some decades to grasp the full significance of Maxwell's discovery. So bold was the leap that his genius forced upon the conceptions of his fellow workers. Only after Hertz had demonstrated experimentally the existence of Maxwell's electromagnetic waves did resistance to the new theory break down. But if the electromagnetic field could exist as a wave independent of the material source, then the electrostatic interaction would no longer be explained as action at a distance. And what was true for electrical action could not be denied for gravitation. Everywhere Newton's actions at a distance gave way to fields spreading with finite velocity. There's interactions at a distance which don't. Because the actions at distance are basically statics. Meaning the motion of a magnetic field in a permanent magnet is according to the kinetic motion of the body, which has encompassed within its realm, its region, its configuration space, magnetic field. It's material points. It's rigid body. So, back to Einstein. Of Newton's foundation, there now remained only the material mass points subject to the law of motion. But J.J. Thomson pointed out that an electrically charged body in motion must, according to Maxwell's theory, possess a magnetic field whose energy acted precisely as an increase of kinetic energy to the body. The electromotive force, the electromotive potential, EMF, voltage difference, voltage potential. If then a part of kinetic energy consists of field energy, might that not then be true of the whole of the kinetic energy? This is that magnetic fields are rigid at all. And so it's not an unfamiliar concept by itself, like the magnetic bottle, or that according to current, in systems of current like alternating current and direct current, that the magnetic field is established and then it interacts with magnetizable or media according to its various regimes of magnetism: ferromagnetism, ferromagnetism, paramagnetism, diamagnetism, antiferromagnetism, antiferromagnetism, ... These speak to the many lettered fields and of potentials in the electrical and magnetic fields, plural. But here, that's back to Einstein. A part of kinetic energy consists of field energy. Might that not then be true of the whole of the kinetic energy? Perhaps the basic property of matter, its inertia, could be explained within the field theory. In a sense, when it's only observable. The question led to the problem of an interpretation of matter in terms of field theory, the solution of which would furnish an explanation of the atomic structure of matter. Soon realized that Maxwell's theory could not accomplish such a program. Since then, many scientists have zealously sought to complete the field theory by some generalization that should comprise the theory of matter. But So far, such efforts have not been crowned with success. In order to construct a theory, it is not enough to have a clear conception of the goal, though it is advised. One must also have a formal point of view which will sufficiently restrict the unlimited variety of possibilities. So far, this has not been found, according to the field theory. Accordingly, the field theory has not succeeded in furnishing a foundation for the whole of physics. For several decades, most physicists clung to the conviction that a mechanical substructure would be found from Maxwell's theory. But the unsatisfactory results of their efforts led to gradual acceptance of the new field concepts as irreducible fundamentals. In other words, physicists resigned themselves to giving up the idea of a mechanical foundation. These are because the electrical fields and current and their changes act in these super in flux terms, and bradyonic and tachyonic flow and flux terms. That these things are what to get figured out, how alternating current works. These days we talk about electron holes because electrons don't, there's electron drift, but mostly the current in terms of going, a light speed is like a hole propagates, there's a shifting back and forth, and so what ends up happening is that ripples go through, and these represent the crests of signal amplitudes go through in terms of continuous waves, basically reflecting that there is a lot going back to this mechanical bit, or what drives the thing in terms of the field is established, because anytime you establish a field that simply has relativity in the absolute, then it basically makes for another entire one of Einstein's fields, and including all the space, and including the metrics that's about it, these different central symmetries. The central symmetries and origins are these whole kinds of things, and affect frames with import of other concepts of the field. But it is so that these days that there's the idea that physics is a field theory, and physics is a gauge theory, which is a field theory, about the curvature and the gauge, and the metric so associated with it, our gauge, the real gauge, our gauge, that these are the kinds of things that get into where the foundations is at. Thus, physicists held to a field theory program, but it could not be called a foundation since nobody could tell whether consistent field theory could ever explain, on the one hand, gravitation, on the other hand, the elementary components of matter. In this state of affairs, it was necessary to think of material particles as mass points subject to Newton's laws of motion. This was a procedure of Lorentz in creating his electron theory and the theory of electromagnetic phenomena of moving bodies. Such was the point at which fundamental conceptions had arrived at the turn of the century. Immense progress was made in the theoretical penetration and understanding of whole groups of new phenomena, but the establishment of a unified foundation for physics seemed remote indeed. And this state of things has even been aggravated by subsequent developments. Development during the present century is characterized by two theoretical systems essentially independent of each other: the theory of relativity and the quantum theory. That's still so today. The two systems do not directly contradict each other, but they seem little adapted to fusion into one unified theory. We must briefly discuss the basic idea of these two systems. So then, that's for reading some more later, I suppose, because we've just read Einstein's more extended chapters on quantum mechanics, the theory of relativity, physics and reality, with many sections, including classical mechanics, theories of relativity, and theories of quantum mechanics. And the discussion that it's really that physics is owed by mathematics models sufficient for the infinite and infinitesimal continuum dynamics, the continuum mechanics, to write quantum mechanics and the theory of particles waves as a theory of some potentials, a theory of sigma potentials that are the real fields. After that, we've already had quite a bit of discussion about what are mathematics as fields and what are physics as fields, the definitions. That is still rather striking, though, that even still today, because gravity is left out, and that relativity mostly doesn't have a theory of space contraction yet, and it doesn't have a mathematics that really makes tractable the usual types of applications for the rotational mass energy equivalents and these kinds of things. there's really quite a bit missing, and otherwise some of the imports of the theory, like light speed, it's a law, and this kind of thing, which these days the Sky Survey is showing that there are apparently superluminal jets of highly dynamical relativistically systems, makes it so that there's on the one hand that the entire apparatus of science is written out that, you know, we live in a static universe and things are unchanging over time, basically. This is a placation. It's placatory for all kinds of things with regards to the terrestrial and the mechanical and the empirical, that then as well having a theory with gravity in the middle basically ends up requiring some kind of quantum, but continuous really, you know, fall gravity and this kind of thing, that the models would not be the same with regards to the transmission of information faster than c. The idea is that no, you cannot transfer information arbitrarily as faster than light's speed in a vacuum. But you can contrive an arbitrarily large experiment and build it over the years that it would take to reach light speed, that then it's possible to make an observation in the gravitometric. It's possible to establish either way what happened, because that would be a result of a long experiment. So this way, then it can be discussed how these kinds of things can happen without violating other known laws of physics, without making it so that everything else breaks down. While at the same time making it so that it's no longer deemed hypocritical that space-time is curved, and also it curves instantaneously everywhere at once. It's always current, because otherwise then that would just be wrong. And so there's some interpretations of this otherwise sound, consistently logically theories that are parochial and wrong. And there's some kinds of these implementations of the experiments, the configuration, that are highly contrived to leave those things right. And really the searches in the physics are two things. One is establishing the precision of the experiment, establishing that it's correct and matches expectations. Then the actual search for new physics is usually left to people who only would already know. So it's no use disturbing society and making them think that physics was wrong, because then that would make them, you know, skeptics or cynics and worry. But at the same time, it's like when the Higgs boson was discovered, and it's the last particle you need to make all the standard model of particle physics. Well, it's also the first non-standard particle. And here's why. Because they found the boson and it has a big divot in the middle. When people heard that, they were like, I never heard or thought about that before. And it's like, well, no, you didn't. And you don't need to know, because if you can't figure it out by yourself, then what's the point of telling you? Because then you might get that wrong. Just, you know, stay in your lane, that kind of stuff. While that's so, foundations basically has no conscience with regards to that. Its only conscience is with regards to the completeness and the consistency of these things, and then the correctness, as Einstein puts it, thus that you need to be able to determine what is follows the defined and derived, and not just that one of any multiple worlds might be correct, but that this one is, and why, and all the question words, why, answered, or what. And so this is part of the foundations and the study of foundations. And so Einstein's always already given us a very rich gift in terms of his final edition of his theory of relativity that's logically much less attached to some of the things, and doesn't say necessarily so much about other things that have been traditional interpretations, and which are largely validated because then otherwise they are not invalidated just because they're outside of the realm of the configuration of the energy experiment. And that there's basically that the derivations that then are added up to make it so that what he has is so are not usually designed to find new physics so much as to find out if it'll be correct to keep using the existing physics. It's the same with quantum mechanics. So that said, there's a lot more to be said for dynamics in this field theory, while at the same time we attain to this real true foundation, which is a great thing. And as he put it, it brings to arise the passionate zealotry of people whose basically biggest admiration is the world of thought. And so that's something that is a very strong reason that Einstein is a model physicist and a model philosopher for this, a man of science. And also that because then he's also lionized as the man, and one of the greats. That then anything that so follows from society's adaptations and reactions to both correct and incorrect or improper interpretations of his theories fall back on that. So yeah, a lot to be read from this Einstein's out of his later years is a defense of his theories and a gift of a restriction of the theories and a proviso of his desidera and requirements for a greater theory, foundations. And then also, as was noted, a defense from his own followers who, right or wrong, have picked up nonsensical extensions to the theory. And the same goes for quantum mechanics and quantum physics as well, which is, again, a continuum mechanics. S must sein, or it must be, according to these various Platonist ideals, that is so. So by now, this has been mostly pretty much my opinion, but it's not one that I couldn't directly derive again from the philosophy of science and this philosophy of theory, and theory at large. So these are the kinds of things that make it so that being able to pick up and put it down and only necessarily need to reread this section of the theory of philosophy of logic and mathematics and philosophy of statistics and science that is self-contained in that sense. That's one of the greatest things about it. Vis-a-vis, like belief systems that basically are unique. The phenomenological, besides that the sense experience is so vital for physics to make it relayable, that everybody has their own sensory phenomenology. It's unique. And it can't be replaced. So it gets to that the only form of the interchange of the ideas is scientific. And that otherwise it's the weaker forms of metaphor, which are weakest with regards to fallacies and these sorts of things which result the improper application of logic or the manipulation. That the manipulation is deemed fundamentally wrong, and because it can only involve a half-truth of a sort at best, that the rhetorical, though, need not be manipulative, because as a conscientious scientist and a conscientious logician and mathematician, there can be shared a common take it or leave it, free of strings theory, and all the necessary apparatus to validate it oneself, the development, that this is why foundations is so key, because it represents utterly the conscientious approach to interpersonal communications that are not overly evolved, or as like love and hate was brought into it, or purely phenomenological. They're not exclusive to the extent of that somebody who can pick it up, and that's all there is to it. It's not the esoteric because it's exoteric. Now there's still greater bonds and the greater experience of two people with their secrets and their private experiences together. That fundamentally is unshareable in how that is shared interpersonally. That's a different kind of approach, though, to the notion of learning and foundations. Why it's so relevant to have that for conscientious scientists. Because it's not a lie, nor is it not that it's free of interpretation, but it is interpretation free. Well, I hope this is enjoyable. And again, this has got some of the philosophical part, and not just that, where usually my goals in the philosophical is moralizing, but I've been manipulating that with the rhetorical to basically cast that people who don't adopt these sorts of philosophical approaches mathematically and logically for the sciences and statistics to these approaches and methods are rhetorically vilified. And that's not necessarily just a nice thing, where it's often said, for example, the maxims of the Golden Rule are do unto others as they would do unto you, and then the second one is do unto others as they have done unto you. And then there's the third that besides this very notions of egalitarianism and fair play, then that the ethical and moral basically ascribes to the higher good of the common and this kind of thing.